that is R.K. Bansal. इसमें बहुत अच्छा वाइड कवरेज दिया है. लैंग्वेज इज वेरी इजी and it is designed as per our RTMNU syllabus. Again, R.K. Rajput is studying on the same methodology. F.M. White and K.L. Kumar is considering more mathematical problem, and the coverage is quite different with the Bansal and Rajput. It is quite a wide range of book. इन चारों बुक्स की जो मेथोडोलॉजी है, जो अप्रोच है, वो टोटली डिफरेंट है. सो आई सजेस्ट यू whenever you refer, just go with any of the one book or just finish off with the one book, then go for the another one. Okay, चारों बुक को एक साथ लेके बैठना है, चारों को एक साथ रेफर करना नहीं. ठीक है, just refer R.K. Bansal if you are preparing for RTMNU syllabus, and you may go with the Whites and Kumar if you are preparing for the competitive examinations. Okay, we have completed our fluid properties, that is density has been covered. So next property is your specific gravity. So density is nothing but your mass per unit volume. Okay, more denser the particle or more denser the specimen, more will be its density and more will be its mass. Specific gravity is your ratio of density of fluid to the density of water. Now here, now we know the definition. यहाँ पे एक trick आता है. In examinations, you are given with the specific gravity and you have to find out the density, because in numerical you have to supposed to know about the density, but density is not directly given to it. But you know that specific gravity is nothing but density of material or fluid to the density of water. If supposed to be you are given with the specific gravity of mercury, so here you can keep your specific gravity in this formula. You can keep your specific gravity of mercury as 13.5 is equals to density of your material is, you have to find out, and density of water is nothing but we know that it is 1000 kg per meter cube. In case of liquid, if supposed to be you are dealing with the gases, then it will be 1 kg per meter cube. Okay, so here you will directly multiply that 13.6 into 1000, that is 13600 will be your density of material or density of that particular liquid. Then your next property is viscosity. Now viscosity is nothing but the resistance offered by fluid to the flow. It is the internal resistance offered by one layer of fluid to the another layer, or simply in simple language we can call it as a resistance offered by fluid which will resist its or which will seize its flow. Now more will be the viscosity, lesser will be the velocity, or thicker will be the material, more will be the viscosity. Both viscosity and velocity are the inversely proportional. Now Newton has given one law which states that your shear stress is directly proportional to the forces of velocity. That is, tau is directly proportional to the du by dy. Here du by dy is nothing but the differential quantity of velocity, and tau is nothing but your shear stress. Okay, when you will replace this proportionality constant, you will get one term over there, that is constant of proportionality, that is your viscosity, dynamic viscosity. So shear stress is directly proportional to du by dy, that is differential velocity in terms of y component, and tau is equals to mu du by dy, where mu is your constant of proportionality, uh, tau is your shear stress, and du by dy is your velocity component or velocity gradient. Okay, here constant of proportionality can be measured in terms of Pascal second, that is nothing but your Newton second per meter square. Why this is? Pascal is nothing but your Newton per meter square second. Okay, this is your dynamic velocity, dynamic viscosity. One more viscosity is there, kinematic viscosity. Kinematic viscosity can be calculated as dynamic divided by density. Okay, here you can see that is mu is nothing but your kinematic viscosity, and it will be calculated as your dynamic viscosity per unit density, and its unit will be meter square per second. Then your next fluid property is specific weight. Specific weight is nothing but the total weight per unit volume. Mathematically, we can uh, write it as a weight of the fluid or liquid to the volume of the total fluid. That is nothing but the W by V. And weight is nothing but your density into G. W is equals to rho into density. Its SI unit is Newton per meter cube. Now specific weight and specific volume. These two terms are inversely proportional. So specific volume will be your volume of fluid per unit mass. That is, it is a reciprocal of your density. Density is nothing but mass per unit volume. So specific volume will be volume per unit mass. Its unit will be meter cube per kg. Specific volume, specific weight and density. All these three relations are interconnected. If you will come to know, or if you are given with any quantity of either density, specific volume or specific gravity, then by using the intercorrelation formulas you can find out the other quantity. Then there is water pressure and surface tension. Now pressure is nothing but the pressure exerted by the vapors in the equilibrium state. It's supposed to be, I'll take a container and I'll cover that container by the lid, and you are giving a temperature to that container. What will happen due to the change of exchange of heat? The molecules from the surface will try to evaporate on the surface, but as because of there is a coverage of lid, the pressure will exert on a water. So that pressure will become or will be called as your vapor pressure. Next quantity is your surface tension. Surface tension. Yes. Can you see this figure? Now to understand the phenomena of surface tension, just consider two molecules. One molecule of water is inside the water or inside the liquid, and another molecule of water is on the surface. So what will happen when body or when the liquid is at rest? The molecule which is inside the water have all types of cohesive forces in all possible directions. The single molecule will exert a force in all four directions, but the molecule which is at surface will only exert a force which is in downward, because there is two types of forces. One is adhesive and another one is cohesive. Adhesive force is from outside pressure and cohesive force is from the inside of liquid. So the molecule which is inside of your surface, that will be in an equilibrium state, but the molecule which is at the surface will have only a downward force. That is nothing but your normal force, normal tangential force. Now this normal force will try to pull your surface downward, but here the molecule which is in equilibrium will not exert any sort of force. So all the members or all the molecules, atoms which are situated on the surface of this liquid will try to pull this water or try to stretch this membrane into the downward area. So what is happening? This free surface is behaving like a stretch membrane because there is only inward force. The outward molecules are not trying to pull out it of the surface, but the inward force is trying to stretch the membrane into the inside of the water. Because of it, what is happening? The area will going to be minimized, or the surface will try to pull inward. So what is surface tension in free language? When the free surface behaves like a stretch membrane and it will try to minimize its area, this phenomena is termed as your surface tension. Now see what will happen if supposed to be you are considering a ball. Okay, so outside the ball there will be a different material, a different state. But inside of the ball there will be a different state. So the inside of the water bubble or the ball will try to shrink that membrane from its original size and shape to the new size and shape. So what will happen? The area of the ball or the bubble will reduce to a new area. So there will be change in state. So by change in state, there will be a new term will come into existence, that is termed as your work done. So work done of that contracting surface will be equals to your surface energy, or you can call it as a surface tension. Okay. Now here see, surface tension can be calculated as, it is defined as mathematically as force per unit length. Here supposed to be I am telling this, if these molecules are contracted by, so this force divided by its surface length will be termed as your surface tension, and its unit is Newton per meter. Here I had taken three examples of surface tension. One is your water droplet, soap bubble, and water jet. Now see carefully, when you are considering a water droplet have only one surface of water, that is inside of it, and only one open surface, that is outside of the droplet. Then you are taking a soap bubble. Soap bubble is having two surfaces. One is inside and another one is outside surface. Then there is water jet. Again, water jet is having only one surface, one outer surface. Okay. So when you are considering water droplet, here you have to, what is happening? The inside pressure must be equals to the outside pressure for the equilibrium. Okay. So supposed to be I am taking inside pressure as Pi, that is the P inward or P internal pressure, and PO will be a P outward or P outside pressure. Okay, so total equilibrium pressure can be calculated as a inward pressure minus outward pressure. Okay, so to study this bubble, to study this droplet, I have cut it down into the part, and your inside pressure is Pi and outside pressure will be PO. Okay, so Pi must be equals to your PO for the equilibrium condition. So how will you calculate Pi? That is the pressure into area. Okay, that will be total force for the equilibrium, and same pressure into area, that will be a total force for the equilibrium at the outside. Now we are considering the inside of this water droplet, so pressure is Pi into its area will be pi r square. Okay, and when we will equate this to the outside pressure, so its pressure will be sigma into its surface area will be 2 pi r. So when you will equate these two terms, you will get your excess pressure is equals to 2 sigma by r. That is 2 into surface tension divided by its radius of the droplet. Same if we'll consider the soap bubble, here also you will compute or you will equate the outside pressure to the inside pressure, and difference between these two pressure will be your total pressure, total exerted pressure on that particular body. Okay, here your pressure will be P into pi r square for the inside, but here for the outside it will be 2 into 2 pi r. Why this so? Because this bubble is having two surfaces. Okay, so here sigma into 2 into 2 pi r will be come into picture, because यहाँ पे हमारे पास दो surface है, one is inside and another one is your outside. So here your excess pressure will be 4 sigma by pi. Same with the case of water droplet or water jet, your pressure will be sigma by r. Here your inside pressure will be sigma in P into 2 pi r, and your outside pressure will be sigma into 2L. So here you will get a total surface tension is equals to P into R, or total pressure is equals to sigma by R. Okay. Now here question may be asked that what is the pressure difference or surface tension for this water jet, either for the soap bubble or either for the water droplet. There may be direct question or there may be indirect question. Yeah, you can directly ask with the three different quantities of the surface tension, else you are given with the force and length, and you have to find out the pressure differences in terms of P. Okay, so for water droplet it will be 2 sigma by r, or soap bubble it will be 4 sigma by r, and for water jet it will be sigma by r. Next property of your fluid is your capillarity. Now capillarity is nothing but rise or fall in the liquid when it is exerted in a small diameter as compared with the larger diameter. If supposed to be you are having a larger diameter pipe or larger diameter uh, container, in that if you have exerted a small diameter container, then there will be either rise in the water surface or either fall in the water surface. Now this rise or fall will depends on the cohesive and adhesive properties of the liquid which is inside as well as outside of that particular container. If supposed to be so, if the molecule is having greater adhesion or cohesion, then it wet the solid surface and result in capillary rise. If example, we will take water in glass tube. Okay, so in water, if water is there in a glass tube, there will be rise in the liquid surface because of its higher adhesive properties than the cohesive properties. That is, the outside pressure is more as compared with the inside pressure. Okay, so here we have finished with the fluid properties. Fluid properties, there are 6 to 7 types of fluid properties. That is just density, specific gravity, specific volume, mass density. Then there is capillarity, surface tension. Okay, in that there is correlation between density, specific gravity, and specific volume. If one of the quantity is given to you by the correlation, you may find out the other quantity. Then there is next topic we will cover about the fluid statics. Now, in fluid statics, the name itself suggests that the study of fluid at rest or study of fluid in rigid body motion. Now, I had written here a very simple definition. Now, two states are there we have to consider in fluid statics. First state is your study of fluid at rest. When the fluid particle, the liquid is at rest position, that will be considered as a static position. Next position is study of fluid in a body in a rigid body motion. Supposed to be, you just take an example of a bucket. You have carrying a bucket and you are moving with the bucket. So what will happen? You are moving with the bucket, but the water droplets or the water molecules of that bucket are not moving from the position, or they are moving with a constant velocity, which is same as your velocity. So here what is happening? The liquid is in stable condition, but the body is actually moving. Okay, so two conditions are there. First is when the body is at rest, that is, liquid is totally at rest condition. Suppose we are considering an example of your water bottle. Water bottle, your water is in completely stable condition. Second example is fluid in rigid body motion. Supposed to be you are carrying a bucket, in that your water is in moving condition, but that movement is, that velocity is same as your velocity. Here the molecule of water are moving at a constant speed. That is why each and every water droplet or each and every water molecule or atom is in stable condition. Okay, so that condition will also consider as a rest condition. Now see what will happen when body is at rest position. Just assume your water bottle. Okay, in water bottle there is only one force is exerting on that liquid particle or water particle. What is that? That is the inward force, or you may also call it as a inward pressure. So that inward pressure is termed as your normal stress or normal force, because there is no such tangential force. If you consider any molecule of that water container, then or that water molecule, it will have same amount of force in all the directions, in upward, in right, in left, or in downward direction. So what is happening? Each and every molecule is at rest condition. So there is no such work done by single molecule of that water. So that is why only a single force is working on that, and that is what the is pressure itself, the outside atmospheric pressure, number one, and second force which is exerting, it's the self weight itself, self weight of that water itself. Okay, so that both the forces or that both the pressure will come under as your normal pressure, that is the downward pressure. So here two points you have to consider or you have to keep in your mind whenever you are dealing with the fluid statistics. That is, it is the study of fluid when it is at rest. Second point, it is the study of fluid in rigid body motion. Okay, so that body is in motion but that fluid is at rest. And 2 points, just take note of these 2 points. There is no shear stress when fluid is at rest condition. Either the body is moving or fluid is at full rest condition. Second case is when fluid, second point you have to keep in mind is only normal stress will act on a fluid when you are dealing with the statics. Okay, now to study statics in a good manner, you must know, you should have the better knowledge of pressure. So what is pressure? It is the force per unit area. Okay, now if supposed to be I'm telling this, if my force is inclined to the surface, so can I take that full force magnitude? No, I cannot take. So what will be the modified definition? In general, we called it as a force per unit area. But whenever you will consider the pressure, so it should be perpendicular force, or you can call it as a normal force per unit area. Because if the force is inclined, then there will be two components. One of it sine component and another one is cos component. Okay, so you have to deal with the sine component in the downward direction. That is the normal component of that force divided by its total area. Okay, so its SI unit will be Newton per meter square. Newton per meter square is also termed as a Pascal, and its CGS unit is dyne per centimeter square. Okay, question may be asked on the units that what is if supposed to be are given in examination, you are having a total pressure of 1 bar. Calculate the total force exerted on particular body. Okay, and you are given with the area. So you must know that 1 bar is nothing but your 10 raised to power 5 Pascal. Okay, and 1 Pascal is nothing but your 1 Newton per mm square. Again, you may be given with the 1 atmospheric pressure. Okay, so 1 atmospheric pressure is nothing but your 760 mm of Hg. That is 760 mm of mercury. Okay, in that case, you will get answer in mm of mercury only. Again, you can convert this mm of Hg into the mm of water. How this so? By using the relationship between the densities of water and density of mercury. Okay, that or specific gravity. That is specific gravity is nothing but density of liquid divided by density of water. So if supposed to be you are given with the density of mercury, then you can find out the density of liquid and you may go for the pressure. Now see in solid mechanics is nothing but your density is nothing but mass per unit volume. So mass will be your density into volume. Okay. Here everything will be constant. Solid will not change their size, shape easily. They may change, but it will not deform easily. But whenever you are talking about the fluid, at very first slide we have dealt with that we have to consider deformation at each and every point. Okay, so volume will be constant, its mass will be constant, but shape will be continuously changing. So this is what the basic difference between solid mechanics and fluid mechanics. That shape will continuously going to be changed, and you have to consider the deformation in the liquids. Okay, this is what your fluid statics is. Now in fluid statics, one of our favorite topic is the continuity equation. So continuity equation is nothing but your product of cross-sectional area of the section to the speed or the velocity in that particular section. Okay, if you are consider there are two types of section. One is your pipe section or the closed sections, and another sections are your open channels or the open sections. Okay, so wherever you are dealing, there we have to consider continuity equation as area into velocity, area of that section into speed or velocity of the particular section. This is applicable in both the sections, either in closed conduits or the open channels. Okay, so mathematically it is area into velocity must be equal to constant. That is the product of area and velocity at each and every point in a section must be constant as per the continuity equation. If at section 1, I am having area and velocity as given. So at section 2, this must be A2, V2 and their summation should be, or sorry, their quantity or their magnitude should be constant. Okay. If supposed to be you have to derive its derivation. So here I have mentioned that is mass is nothing but your density into volume. Okay. And the total volume, if consider a pipe having a section 1 and 2. At section 1, there will be A1 as the area, V1 is the velocity, and delta x1 I am taking a small part of it. And at the end, there will be A2, V2 as a area as well as velocity, and x2 is your section. Okay. Now here, if supposed to be you have to consider the total volume of a section 1, then it will be A1 into delta x1. And you have to take the volume of second area, then it will be area into third quantity, that is area into its length, that is delta x2. Okay. Now velocity is nothing but change in displacement, that is displacement is nothing but your x or length, you may call it as a, so delta x1 is nothing but your v1 the velocity is nothing but your displacement per unit time, so your displacement will become velocity into time. Okay, so here total volume will be your a1 into velocity into delta t. Okay, here this delta x1 is your total length, here your v1 is velocity and t is time. Same for the section 2, your total volume will be e2 v2 into delta 2. Okay, as we know, rho is the density. Okay, so your total mass will become density into volume, so density into a1 v1 into delta t1. This will be your total mass at section 1, and total mass at section 2 will be a2 v2 into delta 2. Now we know continuity equation is based on the law of conservation of masses. Okay, so as per this law, your mass at section 1 must be equals to mass at section 2. Okay, so we will equate these two masses, so you will get that rho 1 even even delta t1 must be equals to rho 2 a2 b2 delta t2. So as we are knowing, throughout this section there is only one liquid. Okay, so density will be equal, so density will get settled out. Then we will get A1 V1 must be equals to A2 V2 as the densities are same. So in general, you can call it as a area into velocity must be constant, or A1 V1 is equals to A2 V2. Okay. So here one A1 V1 is equals to A2 V2. This is termed as your continuity equation. While deriving continuity equation, we have considered few assumptions, that is flow is steady, it is incompressible, and it is rotational. It is not an ideal flow. Next thing, it is based on the law of conservation of mass. We will just go through few examples. So continuity equation is nothing but A1 V1 is equals to A2 V2. Okay. So if supposed to be you are given with calculate, just go through this example, read out this. Calculate the velocity if 10 meter cube per hour of water flows through a 100 mm inside diameter pipe. If the pipe is reduced to 80 mm inside diameter. Okay, you have to find out the velocity. You are given with the two diameters, that is 100 mm and the 80 mm. So for both the cases, you have to find out the velocity and you are given with the discharge. Okay, so one equation we have, that is area into velocity is equals to the rate of flow, that is the discharge. Q is equals to area into velocity. Okay, so here I have applied this equation for the first diameter, that is area into velocity is equals to discharge. So discharge is 10 meter cube per hour. I have converted it into the meter cube per hour, should be converted into meter cube per second. Okay, so 1 by 3600 से multiply किया है, it should be equals to area into velocity. So velocity we have to find out, that is velocity for 100 mm diameter into pi by 4 d square. So here we'll get the velocity for 100 mm diameter as 0.35 meter per second. And next you have to find out velocity for 80 mm diameter pipe. So again you have to apply same formula, that is q is equals to area into velocity. You will get velocity as 0.55 meter cube meter per second. Now here question may vary, as you are given with the two two pipes with the either same diameter or with the different diameter. But one thing you have to keep in your mind, that discharge will be constant, because A1 into V1 must be equals to A2 into V2. Okay, so on this concept, I have shown one more illustrative example. Just look at it. Water runs through a water main of cross-sectional area 0.4 meters square with a velocity. Calculate the velocity of water in the pipe when the pipe tapers to a cross-section of 0.3 meters square. Okay, I had taken here directly areas 0.3 and 0.4. In exam, there may be chances that you are given with the diameters. So if it is a closed surface, then it will be pi by 4 d square. Okay, so continuity equation a1 v1 is equals to a2 b2. You have to find out u2, that is velocity of your second pipe. So just rearrange that formula and you will get your velocity of second pipe. Okay, so this is all about your continuity equation. Now next topic is on your momentum equation. Now momentum equation is based on the law of conservation of momentum, or you can call it as a momentum is nothing but net force acting on a body, because momentum is nothing but mass into velocity. M into V is nothing but your momentum. So change in momentum, or you can call it as the law of momentum, is nothing but your net force acting on the body. Okay, now we know force is nothing but mass into acceleration. Okay, and acceleration is nothing but change in velocity. That is uh, differentiation of velocity with respect to time. So acceleration is dv by dt. Okay, so your force will become mass into acceleration, that is dv by dt. Okay, so mass of a body is again a varying quantity. So it should be taken into the derivative. So here both the quantities, that is mass as well as velocity, both the terms are varying terms. So your equation for the momentum, or equation for the net force, will be dmv by dt must be equals to the total force. So this is nothing but your momentum principle, that is force must be equals to the varying quantity of mass as well as velocity, which is nothing but your total momentum of the given body. Okay, so this equation can also be written as your function. Force is a function of time, and mass and velocities are the varying quantities. Okay, and this equation f dt, f dot dt must be equals to d mv, is termed as your impulse momentum equation, and it states that the impulse of the force F acting on a ball, acting on a fluid mass m in short interval of time dt is equal to the change of momentum in the direction of flow. In simple language, we can call it as a change in force with respect to time must be equals to the change of momentum in the direction of force, or the total force must be equals to the change of momentum of the body in the direction of force. Okay, then your next topic is Bernoulli's theorem. Okay, before that we have seen continuity equation. Now equation is based on the principle law of conservation of mass. Just keep in your mind, Bernoulli's theorem is based on the principle of law of conservation of energy. Okay, what is Bernoulli's theorem? Bernoulli's theorem is nothing but for a steady, incompressible, irrotational, streamlined flow, the total energy at any two sections must be equal. Okay, just observe this figure and consider any two sections. So the total energy at section 1 must be equals to total energy at section 2. Then, when the fluid is at rest, that is steady, incompressible, and it is irrotational in nature. Okay, but practically this is not possible. So this is the ideal condition. So in mathematical form, we calculate this total energy in terms of potential energy, kinetic energy, and the datum energy. So potential energy is termed as your pressure energy, kinetic energy is termed as your velocity energy, or the energy which is considered or which is associated with the velocity and acceleration, and third one is the datum energy, the energy which is related with the inclination of the surfaces. Okay, so just go through this equation, that is P1 by rho g plus B1 square by 2g plus twice GH must be equals to P2 by rho G plus V2 square by rho G plus twice GH. Okay, so just G will be cancelled out over here. By rearranging the equation, you will get this final Bernoulli's equation. Okay, now I have already told you this is the ideal equation, but in real life or in real practical fluid will not behave as the same. If supposed to be you are having 100 meter of water at the inlet, so you will not get the 100 meter of water at the outlet. There will be 99.9 meter of water at the outlet or 99.8 meter of water at the outlet. So where this water will go? This is this water is nothing but a water loss, or you called it as a head loss. Okay, so whenever you are considering two sections, section 1, section 2. So we will consider that E1, that is total energy at section 1, must be equals to total energy at section 2, plus there is head loss, that is the HL. Okay, so head loss we will consider in when we will go for the further sections. Right now I am not covering the head losses. Okay, but head losses are there at the section 2. Okay, losses will be in terms of the major loss is your friction loss and the electric loss. You can have motor loss जो हम बोलते हैं. Then there are so many types of minor losses are also, like for losses in contraction, losses in expansion, because of bend, because of any obstruction, so more. So what are the limitations? Steady flow, it is incompressible. Okay, so constant energy must be there. An assumption you have written, it is ideal stream flow, a rotational flow, and only the gravity forces and pressure forces are considered. Okay, so by using this Bernoulli's equation, there are so many devices has been made. So that devices are used for the ease or for the calculation of different parameters for the liquid, like velocity, then rate of flow. So first application of this Bernoulli equation was implemented on the venturimeter. A venturimeter is based on the principle of Bernoulli equation. Okay, venturimeter is nothing but a device which is used to measure the rate of flow. Rate of flow is nothing but you can find out the total quantity or the discharge quantity out of the venturimeter. Okay, when you can see venturimeter at your laboratories for the open channels. Yes, in open channels there is venturimeter. Whenever you will go for the open channel practical, just observe the venturimeter. It will have one convergent part and one divergent part, and there is one throat section at the middle of the section. Okay, so it is used to measure the rate of flow, that is discharge. So here again you have to apply Bernoulli's equation at both the section. One is at uh, divergent section and another one is at throat section, that is at the middle section. Okay, and by rearranging the different terms, you will get your discharge formula as A1 A2 divided by square root of A1 square minus A2 square into square root of pi CH. Here A1 is your area of section at the inlet, A2 is area of section at the throat, and H is your total head. Okay, so this is nothing but your theoretical discharge, and practical discharge you will get out of your experiment. Then there is one more type of meter which is again used to measure the rate of flow of the flowing fluid, and it is termed as your orifice meter. Orifice meter is quite cheaper as compared to the venturi meter, but it works on the same principle of the venturi meter. Again, it is based on the principle of Bernoulli's theorem. Orifice meter is a plate type of thing, circular plate is there, which is inserted in between the flow direction. Okay, so again you have to apply, just to derive the discharge formula, we have to apply a Bernoulli's equation at section 1 and Bernoulli's equation at section 2. Okay, at section 1 it will be P1 by rho g plus V1 square by 2g plus z. Again at section 2 it will be P2 by rho g plus V2 square by 2g plus z. That term is same, that term will get cancelled, and at the end you will get a discharge formula as well. Discharge is equals to CD into A0 A1 square root of 5CH divided by A1 square minus A0 square. Here A1 is your area of the section at the inlet and A0 is area of the section at the throat. Okay, and CD is nothing but a coefficient of discharge. Here in venturimeter again you are having the same formula to calculate the discharge. Again here you are having the same formula to calculate the discharge. Both the equipments or devices works on the same principle of Bernoulli's theorem. Then third application of Bernoulli's theorem is your pitot tube. Pitot tube is basically used to measure the, here it is misprint, it is not orifice meter, it is pitot tube, okay? So pitot tube is a device, it's a small bent tube like a device. It is used to measure a velocity at a point, okay? You can place the device at any section, in a pipe, in open channel also, at any haphazard sections also, okay? Just keep that device into the water and you will get the velocity. Again here, to calculate the velocity at a point, we have to derive an equation. So just apply a Bernoulli's theorem at section 1, that is at the water surface, and section 2 is your end portion of the tube or the bent pipe. Okay, so when you will apply Bernoulli's theorem at two sections, you will get a formula for velocity is Cv into square root of 2gh, where Cv is nothing but a coefficient of velocity, g is acceleration due to gravity, and h is your total head. From here you can see that is your total h. Okay. So there may be a question that following are the applications of Bernoulli's theorem, and you are given with the 3 to 4 application are there. You are given with the 4 different example, and in that it's supposed to be Bernoulli venturimeter, then orifice meter, pitot tube. Except that if 4 term will be there, so answer will be that 4 device, which is not based on the theorem of Bernoulli's equation. Okay. Then next there are notches, wears. Now notches and wears we will cover in coming class in brief for a short time. It is defined as a particular device which will reduce the area of flow. So once your area of flow will be reduced, what will happen? The speed of the water will going to increase. It's supposed to be you have to increase the speed of the water, then we will use notches on the dam section or any water section. Now here I have shown B type of section. There may be trapezoidal, there may be triangular section also. Okay, so notches are basically used to reduce the water area and to increase the velocity. So what will be its application? Same with the wears. Wears are the masonry or concrete structure which is placed over the open channel. Notches can be basically seen in the closed conduits also or in open channels also, but wears are specially seen in open channels. Okay. What is application of notches and wears? It will increase the velocity of flow. Once the velocity will increase, what will happen? There will be, we can drop down the velocity to the sudden change. So if there is sudden change in velocity, there will be sudden change in energy. So this change in energy can be stored in particular manner, or there may be formation of a jump. So after formation of jump, what will happen? A huge amount of energy is created, and that energy can be stored. Okay, so to make the artificial jump, there is arrangement of wear and notches. Okay, so here we will conclude our first lecture. So we have covered about the properties of fluid, then about the fluid statics. Then there are two main basic principles in fluid mechanics, that is the continuity equation and Bernoulli's theorem. So in that, all four the topics, Main focus should be on your Bernoulli's theorem and on the properties of fluid. In properties of fluid, there will be definitely one question on the interchange of the properties. You are given with the one property and you have to find out another property. Then in Bernoulli's equation, you are given with the section. You have to apply Bernoulli's equation at particular section, or you may directly given with the two quantities, or you have to find out the third quantity. Okay. So we will continue with our second unit on tomorrow. Just go through it. Thank you.